Now we come towards the origin of X-rays, how the X-rays are obtained, what is the origin of X-rays. Now regarding origin, we can remember like that electrons from the cathode with energy eV strike the atom of the target. Now that target atom absorbs energy, that is electrons in the target atom will absorb this energy, their angular momentum will change and they will jump from lower to higher permitted shell. They will jump from lower to higher permitted shell. When they jump from higher to lower permitted shell, the energy difference will be radiated out in the form of electromagnetic waves, that is in accordance with the Bohr's model. So we come to the main context. Number one is the continuous X-rays. So continuous X-rays are produced by a phenomenon of the Bremsstrahlung, which means breaking or slowing down the radiation. Now in the figure, an atom is indicated. The dark dots are indicating the electron configuration and the wave is indicating the photon. And we are finding that incident electron, they are coming from cathode plate. They reach towards the nucleus, that is the positive charges, and from there they get scattered. So scattered electrons are indicated. So now we find that according to this figure, when accelerated electron strikes a target, it enters inside the target atom. There is an interaction between electron and electric field of the nucleus, producing collision. This results in the loss of energy of electron, and that loss in energy appears as X-ray photon. The energy emitted is Hn or h nu, we can say. Both the symbols can be used. EF is the final energy, EI is the initial energy, where EF and EI are final and initial energies of electron. The electron may suffer several collisions with different nuclei before coming to rest. Many photons of different energy are produced. But however, we will remember like that the wavelength will vary from 10 to the power minus 10 meters to minus 11 meters. Due to large number of electrons in electron beam, we get photons of nearly all frequencies. And these frequencies will vary from 10 to the power 18 to 10 to the power 19 hertz. The X-rays produced in the process of slowing down of an electron are called Bremsstrahlung X-rays or continuous X-rays. So continuous X-rays are nothing. It is simply the process of slowing down of electron by the target. Now we come towards Duane-Hunt rule. Now this Duane-Hunt rule is related to that we equate the energy of electron with the energy of photon. So according to conservation of energy, kinetic energy of electron is equal to maximum energy of photon. So what we have done is we have equated EV naught is equal to h nu maximum, where V naught is accelerating potential difference which is applied between cathode and the target. And from this we get the value of wavelength, that is nu can be replaced and we write C over lambda, and from there we get the value of lambda, that is hc over EV naught. Now the shortcut formula will be 12,400 divided by that is voltage applied between the cathode and the target, and that is directly calculated in angstrom unit. However, we can make the calculation otherwise, that is we can compute the values of H, C, E and V naught, and then we make calculations in meters. After getting our result in meters, that is divided by 10 to the power minus 10, and the result will be estimated in angstrom units. The value of lambda minimum, that is the minimum wavelength, depends only on the accelerating voltage and is independent of the nature of target. And this is what known as the Duane-Hunt rule. Now, one of the part is that if electron is stopped in one impact, then wavelength is emitted, that is called minimum wavelength, or the frequency is maximum, that is nu maximum. Because nu maximum is C over lambda. If lambda is minimum, obviously nu will be maximum. It is the inverse relation. Now another point is, that is no X-ray with a wavelength less than lambda minimum is emitted. So minimum wavelength is 10 to the power minus 10 meters. That is minimum is 10 to the power minus 11 meters. And the maximum is 10 to the power minus 10 meters. That is 0.1 angstrom unit to 1 angstrom unit. Then we can relate lambda with applied potential. If the potential is small, the wavelength generated from the target will be less and kinetic energy will also be less. Nu is always proportional to V naught, where V naught is the applied voltage, and applied voltage is directly proportional to kinetic energy. Now we come towards the characteristic X-rays. Now it is a matter of that a target is made up of which particular material, which is the material used, that is which particular element is used for the production of X-rays. When a target is bombarded by highly energetic electrons, highly energetic means that electrons are accelerated at very high voltage and the energy will be EV. Then it penetrates inside the atom and knocks out electron from inner shells of the target atom. So electron with energy EV, which is very high energy, the electron enters the target atom. It can go up to K shell or it can go up to L shell or M shell depending upon what is the energy of electron. And energy of electron depends upon the voltage. So if we apply a typical high voltage, the electron can penetrate in the atom of target up to K shell or L shell. So various type of X-rays are given out. This vacancy produced is filled by an electron from higher shell. This electron transition results in release of characteristic X-rays. The photon produced when electron jumps from L to K shell is called K alpha X-rays. When it falls from M to K shell, it is called K beta X-rays. The characteristic X-rays produce line spectrum. The characteristic X-ray spectrum is obtained in the form of various spectral series.